All right, let's take a look at the math and science that you're going to need for understanding this course. So, first thing we need to talk about is graphing. There's lots of graphs in economics. If you talk to people who hated economics, one of the things you're going to hear is like, oh, there were all these graphs and things. And so, it's true that the better that you can understand these graphs, the better you can understand what's going on. Now, the purpose of these graphs is not to make things more confusing. It's actually to make things a little simpler to understand. So the first thing let's talk about is slope. Now, from Algebra 1, you might remember like slope is change in y over change in x. It's basically showing the rates that these two compare with each other. How the rates change with one another. And an important thing to understand is that slope has units, okay? So whenever we're dealing with scientific things, the slope is never -5. The slope is never 1. There's always units involved with both the y variable and the x variable. So for example, look down here. We've got two variables. We've got price and hamburgers demanded. Okay, this is our y, this is our x. So if I say that the slope is -0.02, that's not enough. That doesn't help you make sense of what's going on here. What the slope is it's -2 cents per hamburger. Okay, so as we get one additional hamburger, the price goes down by 0.02. So if I was to interpret this in terms of like demand, to increase hamburger sales by 1, okay, again, change in 1 here, we must reduce the price by 2 cents. So a change of 1 hamburger needs a change of 2 cents. Okay, so everything, every slope that you see is going to have a meaning, an interpretation. Okay. Of all the things we're going to talk about, this next one is probably the biggest one, which is that graphs in 2 dimensions can show a change in a third variable by shifting. Now here's what I mean. So look at this solid line right here, and let's say that this shows the relationship between the price and the hamburgers demanded. Well, let's say we raise the price. Okay, well that's already one of the variables in our model. So if I raise the price, then I'm just moving along this line. If I lower the price, I'm also moving along this line. But what if I change another variable that's not price, that's not hamburgers demanded, but it has a effect and it changes this relationship? So for example, let's say something comes out and it says, oh wow, hamburgers are really unhealthy for you. Here's a much better alternative. Then this relationship, this entire relationship is going to change. So at any price, the amount of that we demand is going to change. So the entire line shifts here. All right. And the same thing if we increase. So again, movement along the line is caused by one of these two variables changing. But if that line moves, then what that means is that some other variable has changed it. Okay, so we can show a third variable by shifting this 2-dimensional graph. All right. Sometimes we can see important quantities on these graphs. So let me give you an example. Let's say that I have this price and quantity, okay? And we can basically figure out how much revenue they get. I didn't color it in here, but this big rectangle right here represents how much total revenue that the producer is giving. Like if I sell 50 and I charge 250, and the total amount that I make is going to be equal to this area right here, 50 times 250. Okay, but let's say the price used to be $2. Well, then this rectangle represents my amount of revenue. But also, let's say that 50 cents is all coming from this new tax. So, I go from 2 to 250, and I'm selling 50 of the quantity. So this rectangle right here represents the amount of revenue that is going to taxes, because it's 50 cents times 50. So what I'm basically trying to say is that, especially rectangles, they represent multiplication. And we can see these multiplications on these graphs. Why are we looking at these graphs? Why can't we just multiply numbers, Mr. McClung? You're just making things complicated. No. The idea is, when we start drawing these graphs, we're going to start shifting things, and some things are going to get bigger and some things are going to get smaller. So when we start drawing these graphs, you're going to see, oh, the revenue gets bigger. Oh, the tax gets bigger. Oh, the profit gets bigger or smaller. We can see all of these things visually so we can understand it better than if we were just like looking at a bunch of numbers trying to understand what's going on. So this is going to happen a lot in econ, where different areas on the graph represent different things, and as they grow and as they shrink, we can see visually what the impact of some of these policies will be. All right, the formula you will use most in this class, this will come up over and over again, you will eventually memorize it just by using it, is the percent change formula. Percent change is basically change over the old value. So new minus old over old, and then to change it to a percent, we multiply it by 100%. So for example here, if the price goes from here to here, we take our new value minus our old value divided by our old value times 100. Okay? Another important thing to know how to do is dimensional analysis. Dimensional analysis, hopefully you've had some experience with this in science. Dimensional analysis is basically converting one value to another value using conversions. And the way this basically works, let's say I'm trying to convert dollars to pounds, okay? Or pounds to dollars. Well, if I start with pounds, and I know, okay, so I have 230 pounds, and I go, okay, I've got $1, which is worth 76 pounds. I can use this conversion by multiplying it appropriately. Now, if I've got pounds here, then pounds needs to be what I'm dividing by. Pounds divided by pounds will cancel out. And dollars needs to be in my numerator, and that needs to be what's left over. So basically what happens here is it's 230 times 1, which doesn't do anything, divided by 0.76. Essentially what this does most of the time is it just helps you remember, am I supposed to be multiplying or do I need to be dividing? So sometimes you can figure this out without dimensional analysis, but it just makes it a lot easier to keep up with the units and keep up with, am I supposed to be multiplying, am I supposed to be dividing? All right, this next bit is more of a science thing than a math thing. There's going to be lots of times where we are talking about things that are correlated, and it's very important that you understand that correlation doesn't mean causation. If you haven't heard this yet, this is a big, big, big deal. Not just in science, but just kind of in life. Just because things line up a certain way doesn't mean that one thing caused the other thing. So there's many ways that two things will look like they're correlated, where one isn't causing the other. One example is reverse causation. Reverse causation is when someone thinks that this is causing this, but it's actually the other way around. For example, a lot of people will look at certain data and say, oh, well, an increase in policing actually led to an increase in crime. Now, while that's possible, maybe the more likely explanation is communities often respond to increased crime with increased police force. So the causation was backwards. So that's reverse causation. Lurking variables happen very, very, very often where you have two variables that are both impacted by a third variable, a lurking variable. Now, an example, they actually found that in many countries, the number of TVs per capita is actually more predictive of good health than number of doctors per capita. What? Okay, so we don't need more doctors, we need more TVs? Like, what's going on here? Well, it turns out it's not the TV. It's if you have a TV, then that requires, some good infrastructure. If you have good TVs, there's a decent chance you also have good plumbing and other, infrastructure that you need to have television. So it's not TVs are causing good health. It's good infrastructure leads to more TVs and better health. So it's actually this third variable that's actually, the causal factor here. There's also something called bidirectional causation. Now, these are interesting scenarios because instead of this causing this, it's actually this causes this and this causes this. There's kind of a feedback loop there. Okay, and the example that I listed here is poverty leads to crime. I would say that is fairly true. If you have a situation where you have poverty, it's going to increase the crime rate in those areas. But we can also say the reverse, that if you have more crime, if you have people going to jail, if you have communities where people are stealing and killing around you, that's going to also lead to poverty. So you have this kind of feedback loop. And one of the things that makes this important is that if you're going to tackle one of these problems, you kind of have to tackle the other problem at the same time. Because if you only tackle this one, then the other problem, if you leave it, undisturbed, is going to feed back to the other and cause more problems. And my favorite is this one. Coincidence. Sometimes, especially when you're looking at time series data, whenever you're looking at along a timeline and going, oh, well, this happened and then this happened. One of the jokes that I used to make with my students, I started teaching around 2006. And then a couple years later, the economy collapsed. So what does that mean? That means that Mr. McClung teaching caused the economy to collapse. Now, of course, this is ridiculous, but we do the same thing when it comes to certain laws being passed. So-and-so was president, and so we say, oh, well, because this happened and this happened, then it's this, it's the fault of these policies, where in time series data, that's not a very good way of looking at things. You really have to control for a lot of variables. One of the best natural experiments you can do is when you look at policies being enacted at different times, and you go, oh, well, this policy was enacted here, and then this happened. And over here, this policy was enacted here, and this happened. So you're dealing with things at different times, so you're able to make a more fair comparison. But a lot of times, you just go, oh, well, that's just a coincidence, okay? So these are some of the big math and science concepts you're going to need. We're not going to dig too deep into the math or the science, and we will always go over formulas and stuff, but I wanted to get into some of the big ideas before we dug in.